What I'd like to do here is to solve this problem for you. I'm going to read it to you. It says, a cruise ship traveling west at 5 meters per second realizes it is late and so accelerates in the same direction at 0.25 meters per second squared. In 3 minutes, how far has the ship traveled? I'm going to solve this in full detail, and along the way I'm going to be explaining some tips that I think you would need to know if you're going to be successful in other similar questions. So step one for me, I think is always so critically important if you can visualize the problem. If you can't actually picture what's going on, then you simply have no hope of being able to solve it. So even if it's a simple image, I think it's important to try and draw something. So here, let's draw a cruise ship. Okay, there's smoke coming out. There we go. And here's our water. And what do we know about this cruise ship? We know that it's traveling west at 5 meters per second, and that it's going to accelerate in that direction, and we wonder how far it's going to go in 3 minutes. So here's my image of what we need to focus on. If step one is to draw an image of it, then step two is to identify what is known and what is not known. Okay? Now in all these kinematics equations, you're typically going to have these 5 variables: delta d, displacement, initial velocity, final velocity, acceleration, and time. I want to note that if you haven't noticed already, that every time I write these symbols, things like delta d, I'm putting an arrow bar above it, acceleration, okay, we call it an arrow bar, across the top, and that's because it's indicating that this is actually a vector quantity. Alright, it's not a scalar, and if you can't remember what that means, then I think you might need to Google it or go back to one of our earlier lessons to understand the difference between vector quantities and scalar quantities. In the meantime, let me erase that. So let's look at what we know for each of those variables. So I'm going to rewrite them all again, and we'll identify the variables as we go. Displacement. Do we know how far that the ship has traveled? Well, the answer is no, and in fact, if you look at the question, this is really what we're being asked to find out. So I'm going to put here that we need this. Initial velocity. Do we know how far it was traveling? Yeah, it was traveling at 5 meters per second west. We know that it accelerates, but we aren't told how fast it accelerates up to, so final velocity is unknown. Acceleration is given at 0.25 meters per second squared, also in the west direction because it tells us it's in the same direction, so we got to keep track of our vectors there. And finally, we know that the time it takes was 3 minutes, and we have to make sure that our units all match, and since everything else has been written in meters per second, we know that 3 minutes times 60 seconds apiece is going to be 180 seconds. Okay? So let's take that information and we'll stick it off to the side because this is what we're going to refer to. Now, if you've gotten this far in a kinematics equation or a question, you have almost entirely solved it because the next step is really just to choose the tool that we're going to need in order to solve what we want to solve. So if you'll look at this, we have information for time, initial velocity, and acceleration. We don't know anything about final velocity, and we need to find displacement. So in simple terms, we need to find an equation that allows us to solve for d, but that does not include VF in it, because if it has VF in it, we have no action we can take. So that's easy enough to do. That I know will work is this one. Displacement is initial velocity times time plus 1/2 acceleration times time squared. Let's put that off to the side. And let's substitute in what we actually know. So in this case, let's put in our values. Initial velocity was 5 meters per second west. For the time being, I'm going to leave the vector notation in. I'm going to leave that the letter W because I'll change it into algebra later. We know that it traveled for 180 seconds plus 1/2 the acceleration, 0.25 meters per second squared west, again, times 180 seconds squared. Okay, now let's take our vector notation, anything that's been written in letters, and we have to turn that into algebra. So we know that east is positive, west is negative, so what we can end up with is delta D is going to be equal to -5 times 180 plus 1/2 negative 0.25 times 180 squared. And now we just need to start crunching some of the numbers. So displacement, we have -5 times 180, that gets us -900. And this is going to be plus, and let's run these numbers. We have 0.5, so 1/2 times 0.25 for the acceleration, multiplied by 180 squared, gives us 4,050, so -4,050. Okay, we can simply add those numbers together to find out that delta D is going to be equal to -4,950 meters. Now, because the question was given in vector notation, I don't really want to leave it in this algebraic notation with the negative sign. I know that negative means west, which means I can finish the question by saying the displacement is going to be 4,950 meters to the west. Okay? And in general, it's just good for a statement that says, therefore, the ship travels 4,950 meters west in 3 minutes. Okay, I want to point out to you that I have not actually rounded my answer to significant digits because we're just getting used to the idea of significant figures and significant digits. So for the time being, I'm going to leave it there, and we can worry about rounding in the days that come. Okay, so we'll stop there, and hopefully that was useful.